Okay, so we're gonna try something kind of impossible. We're going to explain all of physics. You know, the fundamental rules that run everything, from why your phone hits the floor to the very beginning of time itself. And yeah, that's a huge topic. But to get our heads around it, we just need to start right where we are, right now.
So, let's just start with a simple, undeniable fact. Right at this very moment, you are on a rock.
A giant one. And this rock, it's not just sitting still. It's literally hurtling through this vast, dark emptiness of space, along with a bunch of other rocks, and planets, and these giant balls of burning gas.
So all of that kind of brings us to the big question, the one that kicks off all of science, really. What the heck is actually going on here? How does any of this work? Well, to find the answers, we need to understand the rules.
And the first person who really sat down and wrote out a universal rule book for all of this was the one and only Isaac Newton. He gave us the basic principles for how everything moves, whether it's an apple falling off a branch or a planet circling the sun.
And it all kind of boils down to this one beautiful, elegant little formula. F equals ma. Force equals mass times acceleration. So what does that even mean? It means that if you know all the pushes and pulls, the forces, acting on something, you can predict exactly how it's going to move. This simple formula made the whole universe seem predictable.
See, gravity's pull gets weaker, and it gets weaker fast as things get farther away. If you double the distance between two objects, the gravitational force isn't just half as strong. No, it's 4 times weaker. This rule, this inverse squared law, is precisely why planets stay in these nice, stable orbits, instead of just, flying into the sun. You know, this actually brings up something people mix up all the time. Mass versus weight. Your mass, that's the actual amount of stuff you're made of, that never changes. Your weight, though, that's just the force of gravity pulling on your stuff. So, hey, next time you're feeling a little heavy, just remember, you're not overweight, you're just on the wrong planet. Okay, so we've got the rules of motion. But what's the fuel? What actually makes anything move in the first place? For that, we've got to talk about the currency of the universe, energy. So energy basically comes in 2 main flavors. Think about your phone. When you're holding it up high, it's packed with stored energy. We call that potential energy. The second you let it go, all that potential energy instantly converts into kinetic energy, the energy of movement, right before it makes that horrible sound when it hits the pavement. All right, now let's talk about the word work, because in physics, it means something super specific. You could push against a solid brick wall all day long, get all sweaty and exhausted, but if that wall doesn't move 1 single inch, you have done 0 work. Physics only counts it if your force actually gets something to move. Sorry, but physics doesn't really care how tired you feel. And this all leads us to one of the most fundamental, unbreakable rules in all of physics. You can't create or destroy energy. It's conserved. When a car slams on its brakes, all that energy of motion doesn't just disappear. It gets converted into heat because of friction. Your brake pads get hot, the air gets hot. The energy didn't vanish. It just changed its form. It moved house. And that brings us to this really weird, kind of profound idea called entropy. Basically, it's the universe's unstoppable one-way trip towards, well, messiness. An ice cube, all nice and ordered, will always melt into a messy, chaotic puddle. It never, ever happens the other way around. And this constant march toward disorder, that might just be the reason time itself seems to only go forward. Okay, so far we've been talking about stuff we can pretty much see and touch. But now we have to dive into the invisible world, the hidden forces, the warped reality that guys like Einstein started to uncover. This is where things get really weird. So, at the heart of everything, from a little static shock to the guts of your smartphone, you've got Coulomb's law. It's super simple. Opposites attract, so positive and negative charges pull together, while charges that are the same push each other away. And hey, sound familiar? Just like gravity, this force gets weaker with distance, according to that inverse square rule. Hold on a second. An inverse square law for attraction and repulsion? That formula looks almost exactly like Newton's law of gravity. This is one of those jaw-dropping moments in physics where you realize the universe isn't just making things up as it goes. It's reusing the same deep, elegant rules for totally different forces. And then this guy, James Clerk Maxwell, comes along and has this absolutely mind-blowing insight. He realizes that electricity and magnetism aren't 2 different things at all. A magnet that's moving creates an electric field, and a moving electric charge creates a magnetic field. It's this constant back and forth, this dance,
that creates a wave that just shoots out on its own, and we call that wave light.
And then came Einstein, and he just decided to rewrite the entire rule book. First, he said the speed of light is the absolute cosmic speed limit, and it's the same for everybody. And for that to even be possible, he figured out that time itself has to slow down and speed up. But he didn't stop there. He then took on gravity itself, saying it's not a force at all. It's just what happens when massive objects literally bend and warp the fabric of space-time.
And from all this radical new thinking came maybe the most famous equation in all of history. 3 little letters and a number that would unlock the power hidden inside the atom and completely change our world.
So what does it actually mean? It means that mass is just a super concentrated form of energy. They're really just two sides of the same coin. This is the secret behind nuclear power. By converting just a tiny speck of mass into pure energy, either by splitting atoms apart or fusing them together, you can unleash a terrifyingly huge explosion or, generate clean electricity for a whole city. Okay, take a deep breath. We've gone from apples falling from trees all the way to the fabric of the cosmos. For this last part, we have to shrink way down to the smallest possible scale, where the rules of reality don't just get weird, they seem to fall apart completely. Welcome to the quantum realm.
Down here in the quantum world, things just aren't definite. A tiny particle, like an electron, doesn't really have one specific location. Instead, it exists in what's called a superposition, which is basically a cloud of probability covering all the places it could be at once. It only picks a spot when you actually measure it.
And to really see how bonkers this gets, let's look at a super famous experiment. You take a single particle of light, a photon, and you fire it at a wall that has 2 tiny slits in it. I mean, common sense says it has to go through one slit or the other, right?
Yeah, that's not what happens. That one little particle acts like a wave, goes through both slits at the exact same time, and then interferes with itself on the other side. I'm going to say that again. A single object was in 2 places at the exact same time. But here's the final twist, the thing that just completely baffles everyone. If you put a little detector at the slits to watch which one the photon goes through, all the weirdness just vanishes. The particle acts like a normal little ball and goes through one or the other. The simple act of looking at it changes the outcome. It changes reality itself. And the biggest question is, why? To this day, nobody really knows for sure. And that right there is the strange, beautiful,